Okay, good morning, everybody. How's your day going so far? So were you able to finish section 9.3 in the lecture today?
No, we did not finish it in lecture.
But I think you started with it.
Yes, we did.
Okay, sure, yeah. So, all right. So if that's the case, then we can devote a big chunk of today still answering problems about sequences. So if you encountered some difficult ones from the from your quizzes or homeworks, send them to me if you have questions via the chat. Oh, also, were you able to see your FRQ results already or not yet? Because we finished it grading Monday night, so I'm not sure if it is already uploaded in CASA. Oh, you haven't? Okay, so just check it probably later today or early tomorrow. But it was already graded. I finished when? I finished Monday afternoon. And the major comment that I have there is, at least for the papers that I graded, there are some parts wherein I don't know how they got to the final answer. So they included the correct solution. Sorry, they have the correct answer and a good chunk of the solution, but some of the middle details are missing. So I don't know how they got from one point to another in their solution. I just assumed and gave them the benefit of the doubt that they did it on a separate sheet of paper but did not include it in the solution. But that will cost them the points which is allotted for the important steps. So, for instance, I hope nobody among you did this, but okay. So say you have a partial fraction problem, right? So you have, say, okay, you have a function here, or a polynomial over a polynomial dx, and then you were asked to integrate this, and then they were able all of a sudden to say, oh, this is equal to 2x minus 1 over the first factors, or say x squared plus 2 dx plus, say, 3 over x dx. And then they carried on with the integration and got the correct answer, the correct final answer. But they did not show how they got the two constants, or yeah, the three constants that goes on top of the partial fraction or the partial fractions. Yes, they must be good at mental math. I don't know, but I still gave them the benefit of the doubt. So maybe they did this on a scratch paper. I don't want to assume the worst case that they just copied it over from some material from the net and so on. But I won't blame any other grader who will think that way. So yeah, so either you lose the points for solving the constants on top, and yeah, you lose the points, which is I think 3 points for the solution for each of the constants. Was it 3 or 6? Um, yeah, so either 3 or 6 points for computing the constants, and or the worst case is your grader will give you a 0 because you did not include all parts of the solution. So yeah, so that I think that's the safest way. Include everything that you can in your solution, and I guess it's also good exercise or a good practice because you learn how to write properly and how to organize your thoughts so that even if your solution ranges to a couple of pages, but you still can organize your thoughts into it, that will be great. And it will also save you some time because if you can do your solution neatly on your actual paper, you don't need to do it on the scratch paper and transfer everything to your actual paper for submission. So yeah, and it will also be better to include all the details as much as you can so that you can get as much partial credit as possible. Because if you did something like this, then I can't give you any partial credit for the steps in between if you didn't get the correct answer. Yeah, yeah, Michael, they said that they also don't have the grades for FRQ yet, but we finished it last Monday, Monday evening. But there's only one person allowed to upload everything on CASA. It's our lead TA, and probably she's still working on it. So just kindly wait for it, probably later this week. But I think it was already graded. So okay, so that's fine. And then some for the trig sub part. I don't know if you well, there's a trigonometric substitution, so you have to integrate some function. Uh, and then they did all the steps, and then they got, say, let's say, sine of theta. Just for example, they got sine of theta plus c. And then remember, to go back to the original variable x, the usual thing that we did is to draw a triangle and assume that, okay, here's my theta. And then based on the substitution statement, you will get the two legs and the hypotenuse. And then based on the SOHCAHTOA, we'll be able to find sine. Okay. Now, I think more than 10 students out of the 97 that I graded did this. So they just said, okay, this is sine of arctan of x over 3, for instance. And then, which is, for me, which is fine. But the next step puzzled me. Because from here, they were able to recover the actual variable in terms of x. So say this is your example, right? So I don't know if there was a very fancy formula that was given in the lecture in order to convert this guy into something like this. So basically, this is what they could have gotten if they have drawn the. But for some reason, they were able to jump from here and go here. If this was an arcsine, then I'll understand because sine is the inverse of arcsine. But sine followed by an arctan, it's not that obvious, at least for me. So was there a fancy identity or form in the lecture? Yeah, sorry, my internet keeps on disconnecting. But anyway, yeah, you should not do this. But yeah, you should not do this, and you're not encouraged to do that because I guess, well, technically this is correct, a sine of arctan of x over 3, but it is not as elegant as what you have gotten if you used this triangle, right? But I know there's an identity. Probably they did it in there, something that you do mentally. So this is something that should be written in paper. So yeah, I hope none of you did that. But there's a lot of them, and that's very suspicious for me. But anyway, but I tried to always assume the best from people. So yeah. Anyway, so as always, once you receive your FRQ part, you will be given a couple of days to take a look at it, and then if you have some questions or you think you should have gotten more points or partial credits for a particular item, let me know. I'll tell you the deadline when for regrading requests. So all right. So now let's go back to our topic, which is about sequences. And I guess we stopped here last time. Okay, hold on. Muriel has a question. Sorry, I think I'm mispronouncing your name, Muriel, ever since. Should it be Muriel or something? Or, yeah.
It is pronounced Morel.
Morel. Okay,
Yes.
sorry about that.
It's okay.
Okay, so you have this question and then you got it wrong.
Yeah,
Um,
I got this one in the practice, not in the practice test, in the test, and I'm
uh-huh.
checking it right now, and it's the only one I'm having suspicions on. I know you can use usub, but could you have been able to use trig sub as well?
Yes, you can use you can use usub for this. And I guess that's the intended answer here. But trigonometric substitution will also work because you have 16 plus x squared, right? That calls for an x equals tangent theta substitution.
Yeah, that's what I was thinking when I did the test. That's why I just picked trig sub. I know now that you can also use usub, but I felt that this question was a bit too
Yeah, because
yeah.
there are more than one ways to answer a more than one way to answer a certain problem, and this
Yeah.
integral can be solved either by u substitution and trig sub. U substitution will be easier, but the question didn't say which one is the best way to solve this particular integral, and even the word best is a little bit subjective, right? But trig
Yeah, I
sub
just
can
thought
be
that the
used for this.
question was a bit too subjective. I know that you don't make the test, but I was wondering if there was a way for me to like put a complaint of some sort.
Yeah, I think you should because you're right. Trig sub is perfectly fine for this. It's just
Which
that we just don't know if the trig sub will lead us to an easy solution, but definitely you
yeah.
can use that. Maybe you can send a screenshot, this screenshot to Professor Almas so
Okay.
that she can decide what to do. And I
Yeah,
guess yeah.
I just thought that maybe if they would say which one will be the quickest, that will be a different story. But because they said best, I don't know. I just
Yeah.
thought that it was a bit too subjective. So, do you suggest I email Dr.
Yeah,
Amos, or
let me just see quickly. So the substitution here would be x equals 4 tangent, right?
yeah,
So if 4 tangent theta, then we'll have 4 tangent theta times secant. And then you'll have a secant tangent, right? So you have a secant tangent. The integral is secant. So actually, it is not that hard at all.
mm-hmm.
So yeah, I suggest you send an email to Dr. Almas and then say, ma'am, I can use trig sub here, and
I think
use
you can
sub is
also
not the exclusive
use
solution.
the integration by parts as well. I mean, that one will obviously be longer, but I will try to send her an email, and maybe if any of my classmates had the same question, maybe we'll get another point.
Yeah, actually, yeah.
Okay.
I suggest you do. And
Mm-hmm.
then you're right. Even integration by parts will work. You let x be, you take u to be x and dv equals the root of 16 plus x squared. Though for the root of 16 plus x squared to get v, you need to do trig sub.
Yeah.
But essentially, IDP will still work. It's just a lot of, yeah, the question is quite big. So,
Okay.
all
If
right.
anybody else
Yeah,
had
good
this
point.
question, please email as well.
Yeah, yeah. So let's do it by the numbers.
Yes, thank you.
Okay, you're welcome. All right, so let's go back to problem 5. I guess this is where we stopped. Did anybody solve this one? I guess we're looking for the convergence sequence n over n minus 5 raised to the 9n. So I guess I started the solution last time. So I said, okay, to determine whether it converges or diverges, we need to find the limit of the n term, right? So we are given the formula for the n. We take the limit as n approaches infinity. And thanks to several theorems that was introduced in the chapter, we now have sort of an analogy between finding the limit of a sequence and the limit of a function in the manner that we used to do it in Cal 1, right? So I suggested last time, okay, this seems to be a very complicated function or a complicated term for the sequence. So let's try to work it a little bit and try to transform it into a function of a real variable. So the change in the variable seems superficial because all I did was change all the n's into x's, right? But I hope it is clear that the significance of the change of the variable is to say that the left-hand side limit here only allows n to take natural numbers as its value, right? And the values for n are 1, 2, 3, 4, 5, and so on. But on the right-hand side, x can take any real number, okay? So actually, I need to change the problem a little bit. I overlooked this technical detail. The sequence will be undefined when n is 5, right? So let's make it a plus. I don't remember if I just invented it over on the fly or did somebody send this, but yeah, the denominator should be n plus 5 so that we don't have the problem when n is equal to 5, right? So here, let's make it plus 5, right? Okay. Oops. So we're taking the limit, and this is what we call the Hitch theorem, in such a way that the limit of a sequence just takes a hitch on the limit of the real valued function. And the good thing about that is that if we know the real valued function, then that is also the limit of our sequence, right? So let's evaluate this limit. Remember in Cal 1, your first approach to limit problems is to try direct substitution first, because functions that we encounter in elementary calculus are nicely behaved at least. So direct substitution might work. So if we do direct substitution, actually x is infinity, so we imagine x to be a very large number, right? So here, we already know that if you have x over x plus 5, that will go to 1, right? Remember, if your numerator and denominator have the same degree, so this is degree 1, this is degree 1, so the limit as x approaches infinity would be equal to 1, just the ratio of the coefficient. So x here has coefficient 1, x here has coefficient 1, so the limit is 1. So the base goes to 1 when x goes to infinity. All right. And I guess we have a similar example before that did that. So we know that, okay, n over n plus 5 will converge to 1, right? Now, but we still have an exponent to deal with here. But when x becomes very, very large, 9x also becomes large. So this guy has the form 1 raised to infinity. And if you remember from Cal 1, 1 raised to infinity is an indeterminate form. All right, I hope you guys still remember that, or at least had the time to take a look at it again. So 1 raised to infinity is one of the, I think, 3 indeterminate forms that involve exponents. So whenever you have an indeterminate form that involves an exponent, the remedy here is to use natural logs or to use logarithms in general. So what we do here is I will let y be equal to our real valued function. And again, we know that the limit is indeterminate as x approaches infinity because of the exponent, right? So what I'll do is to get rid of the exponent, and I can do so by taking the natural log of both sides. Right? And again, at this point, I can use properties of log that allows me to put this exponent down as a coefficient in front of the ln, right? So essentially, I'll have ln y equals 9x ln of x over x plus 5. And then what I'll do now is to take the limit of both sides as x approaches infinity. Because remember, that's our problem, right? But hold on. Let's note that if we will be able to evaluate this limit, what we'll get is the limit of ln y. But what was our original problem? Our original problem is this limit. And this is basically the limit of y as x approaches infinity. But here, at this point, we are geared towards solving the limit of ln y. So this is a reminder that our final answer is not the limit that we'll get by solving this, but we need to do an extra step, right? because this is the limit of ln y, and we're solving for the limit of y. So we'll use whatever value we get here as an exponent to e to get the limit of y. All right. So let's worry about that later, but keep that in mind. So here, when you do direct substitution, you'll have 9 times x, but x is approaching a large number. So the first factor goes to infinity. Now the second factor, ln of x over x plus 5, this guy goes to 1. So basically the second factor goes to ln of 1, but ln of 1 is equal to 0. So we got that, right? And again, if you recognize, hopefully you recognize this to be indeterminate, right? You have infinity times 0, one of the indeterminate forms. So whenever dealing with such an indeterminate form, what we do is to try to write it as an infinity over infinity or a 0 over 0, right? Because if we have an infinity over infinity or a 0 over 0, L'Hopital's rule can be the limit, right? So the trick here is to pick one of the two factors, either 9x or the natural log, and put its reciprocal in the denominator. My suggestion is you pick, you retain the more complicated function as your numerator, and use as denominator the reciprocal of the simpler function. So between these two guys, 9x seems simpler, right? So I'll put the reciprocal of 9x in the denominator. Okay. And note that if you simplify this, you'll get back to the original problem, right? So it's just rearranging the terms. But what's the point of rearranging the factors? Well, now, if you do direct substitution or a direct analysis of what happens on the top and the bottom, the top will still go to 0, right? And then the denominator is this. As x goes to infinity, 9x goes to infinity, 1 divided by a large number will give you a 0, right? And this is a 0 over 0, which is a form that we like, so that we can apply L'Hopital's rule. Okay, let's see. So applying L'Hopital's rule, take the derivative of the top. It's ln of x over x plus 5. So this would be 1 over x over x plus 5 times the derivative of the inside function, but that will require me to use the quotient rule, right? So chain rule plus quotient rule. So low squared, low derivative of the high function minus high function derivative of the low function, right? All over. Hopefully I didn't mess it up. Yeah, kindly let me know, Herson, if you got a different limit here. So hopefully I didn't mess this up. And then the denominator is 1 over 9x. We can look at it as 1/9 of x to the minus 1. So its derivative would be negative 1/9 x to the minus 2. Okay, and we are taking the limit as x approaches infinity. So we'll have what? We'll have the limit of, we'll have negative 1 over 9. Negative 9. And then let's simplify the numerator. So I'll have x on top because of this guy. And then the first factor is x plus 5 over x. And then times x plus 5 squared. And then we'll have x minus x, 5 minus 5. I think I messed the numerator up. I think there should be x. All right, so low squared, and then low derivative of the high, which is 1, minus high derivative of the low, right? So this should be 5. Now I'm seeing the minus 45 that Herson got. So let's see if that's correct. So we'll have, on top we'll get negative 45x times x plus 5 all over x times x plus 5 quantity squared as x approaches infinity. Or actually here, what I'm seeing is x will be canceled, x will be canceled, x plus 5 will be canceled by x plus 5 there. So essentially we'll get limit of negative 45 over x plus 5 as x approaches positive infinity. Now what I'm seeing here is that the limit is equal to 0. But you're saying you got minus 45. Let me double check that. Did I miss something? Oh yeah, I missed this one. This should be minus 9x squared. That means there's an x squared there. And then there is an x here. Okay, there you go. I think it's now correct. Do you guys agree? Let me double check. Yeah, I think this is correct now. And then you're taking the limit of a linear function over a linear function. So basically it's the quotient of their coefficients. So this would be negative 45. And then now, since this is the limit of L and Y, so we say that the limit of our original expression. Let me just copy this. Okay, is equal to e raised to the minus 45, as Herson suggested. Okay, good. Any questions with that? So I hope this brings back some memories from Cal 1, right? Because now it's important that you are able to evaluate limits, at least limits as n approaches infinity or as x approaches infinity. Now, going to Muriel's question. I'm botching your name, sorry. I should study how to pronounce it well. But okay, let's try your question. She's asking about the sequence 2n factorial over n plus 3 factorial. Now, thank you for bringing this up because this is one peculiar sequence because this is defined in terms of factorials. And then the thing about factorials is that they are only defined for natural numbers. There's an extension to real numbers, but that's for higher mathematics courses. So for us, factorials are only defined for natural numbers, so you cannot extend it to real numbers. So you cannot do the same analysis that we did in problem number 5. So all we can do here is to look at the property of this sequence and try to simplify it as much as we can. But let me see. Yeah. So here, you note that an is equal to 2n factorial over n plus 3 factorial, right? And then remember how factorials are defined. So it's going to be 2 times n minus 1 times n minus 2 and so on until you reach 3 times 2 times 1, right? That's how factorials are defined. But be careful about interpreting factorials, because here only n is inside a factorial operator. So that means 2 is not inside a factorial. So n factorial is equal to this guy. In contrast to the denominator, inside a factorial operator is n plus 3. So basically, if you expand the denominator, it would be n plus 3 times n plus 2 times n plus 1 times n minus 1 until you reach 3 times 2 times 1. All right. So basically, n factorial is the product of the first n natural numbers. Here we have n plus 3, so it will be the product of n plus 3, n plus 2, n plus 1 down to 1. All right. And now let's try to simplify and see how this looks like. Note that I still have a 2 in the numerator, but notice that there's a lot of terms that can be canceled, because essentially here from n until 1 will be canceled by these factors over here. Okay, so what you'll get is this. So what's left in the denominator? We'll have n plus 3 times n plus 2 times n plus 1, right? And we can now easily find its limits. So the limit of an as n approaches infinity is the limit of this guy as n approaches infinity. You can translate it to a real valued function, or just say, oh, I know what happens here, because the numerator is just a constant. The denominator increases as n increases. So as n goes to infinity, the denominator becomes a very, very large number. 2 divided by a very large number is equal to 0. So we say that this sequence converges to 0. So in general, when you see factorials, it is not a guarantee that the limit will be equal to 0. So you still need to do some analysis. But the nice thing about factorials, they have a nice expansion. And usually that expansion will allow you to cancel a lot of terms, just as like what we saw here. So if you have factorials involved, then yeah, you just need to manipulate them. All right. Okay. Is that good? Any questions about that? Any clarification? Okay, while you're composing your questions. Yeah, Herson, that can also be done. I just prefer the writing everything in terms of their basic definition and not do something fancy. But I guess you're saying that, okay, so you have this expression, but you'll essentially get the same thing. You can keep the numerator as 2n factorial. And then in the denominator, you can write it as n plus 3, n plus 2, n plus 1 times n factorial, right? Because essentially in my expansion here, I just wrote down n plus 3 until n plus 1, which is basically, I think, what Prof. Almas also did. And notice that the succeeding terms is n factorial. I think this is a cleaner way of writing the solution, but it takes a little bit of being used to factorials in order to realize that pattern there. And that's why you can pull out an n factorial from the denominator, cancel it with the n factorial in the numerator, and got this point. Yeah, I prefer doing the basics and doing nothing fancy about it. So that's why, yeah, I prefer writing it this way. Even until now, I'm working with some very complicated mathematical that has some factorials in them, but I always use this expansion of the factorials because actually it helps me in my thinking process. Doing everything in details, including everything in the solution. I find it really helpful. Okay. All right, so let's see some more problems from the worksheet. Were you able to take a look at the worksheet and find something interesting? Let me see. Okay, probably I'll do some problems that will require some concepts from Cal 1, essentially L'Hopital's rule, limits at infinity. So you'll get a refresher on those topics. So let's see. Oh, since we're talking about factorials, maybe it's a good thing to work problem 29 out. Okay. I'll call it problem 7. I'll just copy it down. This is problem 29 from, it's problem 29 from the worksheet. So here, I guess we cannot simplify this. Let me try. We'll have n squared over n factorial. You'll get n squared on top. We cannot do anything about that. But here we'll have n times n minus 1 times n minus 2 until 3 times 2 times 1, right? That's how you expand n factorial, all right? Now let's see what will happen. Now I can cancel the n's or one of the n's, so we will be having n over n minus 1, n minus 2, until 3 times 2 times 1. Right? And then can we find the limit of this expression? What will happen to this as n approaches infinity? Any idea? So here you can imagine taking the limit of this function. You're correct, Herson. The denominator is getting bigger and bigger faster than how fast the numerator is increasing, right? So I'll mention some remarks about that later. But if you look at it from a purely computational, so this is basically we're taking the limit of the ratio of two polynomials, right? A polynomial in n, technically not a polynomial, but sort of a polynomial-like expression. Degree 1, the denominator is what? Oh, it's actually not. Yeah, I cannot analyze it that way because the denominator is not sort of. It's not like a polynomial per se, right? But the thing here is that the denominator becomes larger faster than how the numerator increases. And Herson's observation is correct. The bottom will get bigger and bigger, right? Because you're looking at the behavior as n goes to infinity. So if you have n here, n is a very large number. But you have n minus 1 here, which is another large number. 2, certainly that will be larger than the n on top. So basically that's a signal to us, oh, the denominator gets large faster than the numerator. So basically the denominator will outgrow the numerator. And so essentially as n goes to infinity, this will also go to 0, right? So we say that the sequence converges to 0. Okay, because again, the denominator becomes large faster than how the numerator increases. Okay, now that's another way of looking at the convergence of sequences. If you see that the denominator, sorry, I don't know what's happening to my internet. Do you experience me cutting in and out of the session? I know what's happening with the campus internet. Yeah, I'm at my office, and yeah, that's why sometimes I keep repeating my sentences. So hopefully that's fine. Uh, there's just momentarily disconnection, but anyway. So this is one, I was saying, this is one way of analyzing. If you have a quotient of two expressions, you can compare the rate at which they changes. So if the denominator grows much faster than the numerator, then the limit is 0. If the numerator becomes large faster than how the denominator becomes large, then there would be no limit because the quotient will go to infinity. If they sort of just change at a proportional way, then the ratio will be their limit. Now, Muriel, sorry, I forgot how to pronounce her name again, but she's asking about this. Let me call it problem 8. Sequence n factorial over n to the n, all right? Okay, let me see if there's a way to analyze it computationally, right? Before I give you a shortcut. So n factorial over n to the n. Let's call it an, all right? So if you expand the top, it's going to be n times n minus 1 times n minus 2 until 3, 2, and 1, right? That's n factorial. Okay, thank you, Morel. Okay, denominator. We expand n to the n. So n to the n is simply n times n times n times, right? Now let's count how many terms do we have in the numerator. In the numerator, I have n factors. In the denominator, being n to the n, I also have n factors. But let's see which grows faster, right? I guess now it's obvious that the denominator, because if you compare term by term, number one, they have the same number of factors, right? Numerator has n factors, denominator has n factors as well. So we can compare each of the factors individually. So it's a contest of which is larger. First pair, it's a tie. Second pair, the denominator wins. The denominator has a larger factor. Third factor, denominator wins again. Actually, the denominator will win again for all the matches, right? So basically, we see here that the denominator grows faster because its individual factors grow faster than the corresponding factor coming from the numerator. So basically, this will go to 0. This will go to 0 as n approaches infinity, right? Because when n becomes large, the denominator will grow a lot more faster than the numerator. Okay, so is that good? So basically, it's a match between which grows faster. Just to summarize before I go to Michael's question, here's a hierarchy of rates of growth, which at least will give you an idea of how fast functions grow as n approaches infinity. So n going to infinity. I guess the slowest would be the logarithms. Okay, and then following logarithms are they're actually powers. So n to the p where p is positive. P is positive. And then following n to the p will be n to the n. N to the n grows faster than n to the p and log n. So if you see a sequence of log n over n to the n, automatically you have an idea that the limit will be equal to 0 because n to the n grows faster than log n. Actually, n to the n is the fastest. I should have written it this way. And let me insert factorials in here. Okay. Factorial grows faster than logarithms, and but it grows slower than n to the n. So just to illustrate this, let's see problem 9. I saw some problem here. Let me see. Okay, let's see problem 35 and problem 41. Let me copy the entire thing. Okay, so let's see problem 35. So problem 35, we have a log of n to the base 2 all over 2n, right? If you go to the hierarchy of rates of growth that I listed here, the numerator is a logarithm, so it is here. It works for any base. Probably I'll say b as any base there, right? So it is the slowest growing function. 2n is sort of n. So definitely the numerator grows faster than, the denominator grows faster than the numerator. So we have a hunch that this converges to 0, right? Because 2n grows a lot faster than logarithm of n to the base 2, right? So if you want to convince me that this, yeah, Morel, you're correct. Slow over fast is equal to 0, right? So, but how do you convince yourself that this is really true? Well, take the limit. So take the limit of log n to the base 2 over 2n as n goes to infinity. Now, top and bottom both goes to infinity, right? Because as n goes to infinity, log of a large number is another large number. 2n, 2 times a large number is a large number. So basically, it's of the form infinity over infinity. So it's calling for L'Hopital's rule, right? So in order to apply L'Hopital's rule, I need to convert it into a real valued function. Just for technical reasons, I'm going to write it like this. And note that this is infinity over infinity, indeterminate form. But that indeterminate form is nice because I don't have to do any preliminary step. So I'll just take limit of the derivative of the top, right? The derivative of the top is 1 over x ln 2 all over. The derivative of the denominator is just 2 as x approaches infinity. And then you can rewrite it as the limit of 1 over x or over 2x ln 2 as x approaches infinity. Numerator is a constant 1. Denominator is or has an x, so that means this will go to infinity as well. So 1 over infinity, that is 0. So indeed, the limit is equal to 0 as evidenced by a tedious application of L'Hopital's rule. But if you know the hierarchy of rates of growth, then you can say, oh, I know that the denominator grows faster than the numerator, and so it should converge to 0. Okay. I think in the exam, you can use the long solution, or you can appeal to the hierarchy of rates of growth. But if you do so, I suggest that you reason out your answer. If you are not, if you intend not to use L'Hopital's rule, probably you can say in your test, okay, I know that this converges to 0 because the denominator grows a lot more faster, not more faster, that's redundant, but it grows a lot faster than the numerator. And hence this should converge to 0, right? So put that into writing and just not say that it converges to 0, because you will not get any credit if you'll just say, oh, this sequence converges to 0. You need to tell me a reason. And a sufficient reason for me is for you to say that, okay, this converges to 0 because the denominator grows faster than the numerator. Okay? Or if you want to be safe, then do L'Hopital's rule, right? Now, problem 10. I hope you don't take if I take 2 more minutes. So, but if you have classes, you can leave and just watch the last 2 minutes of the video recording. But I just want to touch on this problem, say on problem 41. But I guess this is similar to the previous problem, n to the p. Well, Morel, that's not always the case. There are some indeterminate forms that converges. So for instance, this is an indeterminate form. So you have infinity over infinity, and yet it converges. It converges to 0. So it depends on what is the final form of the indeterminate expression. Because remember, we have indeterminate forms whose limit is equal to infinity. If that, it is divergent. But if you have an indeterminate form and it turns out you get that limit, then that will be convergent, right? So I guess this we can say that this converges to 0 because n to the p grows faster than ln n. Okay, so I guess this is sufficient reason for that. Now Michael sent one nice question here. Ln of n squared plus 1 minus ln of n plus 4, right? So we'll try to take the limit as n approaches infinity. Okay, but if you try plugging in a large number, you'll get a large number minus another large number, right? And infinity minus infinity is an indeterminate form. So if that's the case, we need to find a way on how to find its limit, avoiding the indeterminacy, right? So, but here I can apply loss of exponents, albeit in reverse. So basically we'll have ln of n squared plus 1 over n plus 4, right? Remember that if you are subtracting 2 logarithms off the same base, you can write it as a single log, right? They will go inside the common logarithm, but the minuend will go on top, and then the subtrahend will go in the denominator. Okay, and so this guy, we take the limit, but what will happen? Well, what will happen to the inside? Oops. Well, this thing goes to positive infinity, right? Because the degree of the numerator is larger than the degree of the denominator. So the numerator grows a lot faster than the denominator. So it will go to infinity. And then ln of infinity is another large number. So this will go to infinity. So you will have an unbounded increasing sequence here. So you can say that here, the sequence diverges. Because we can't get a finite limit. And then on Morel's question, 12. 3 plus 1 raised to n, you're correct. This is divergent, because if you look for the limit of 3 plus 1 raised to n, actually it's convergent, because here this will just be equal to 4, because if you list down the elements, this will just be 3 plus 1 to the 1, which is 1. 3 plus 1 squared is still 3 plus 1. 3 plus 1 cubed is still 3 plus 1, and so on. So all the terms would be 3 plus 1. If you go to the tail end, we'll get 4, right? Yeah, don't worry, Morels. I was also deceived by the problem. I thought it's going to be a positive infinity. But 1 to the n is indeterminate as a limit. But if you look at it as a sequence, so you see that what happens here is that n goes to infinity, then we'll have, yeah, we'll have a bunch of 4s, actually a list of 4s. Okay. So, I think I missed one question from Michael. I hope Michael is still here. Michael, you sent this one earlier, n factorial over n plus 2 factorial. So I think we addressed it or a similar problem before, but in case you missed it, what you can do here is try to expand the factorials. So n factorial is n times n minus 1 times n minus 2 until you reach 3, 2, and 1. Then n plus 2 factorial is n plus 2 times the number before it, which is n plus 1, times the number before it, which is n, and then you go reverse until you go to 3, 2, and 1. And then you can cancel like terms. Here I can cancel n until the end by this guy. So we'll have 1 over n plus 2, n plus 1 times n. I think this is very similar to the ones we solved earlier. And this will approach as 0 as n goes to infinity, Because the numerator is a constant one, the denominator grows very, very large as n goes large. So that means this will go to infinity, right? So this is divergent. Because we cannot get a finite limit. Okay, guys, sorry I took a lot of time today. But yeah, if you will encounter questions, let me know on Friday. But on Friday, we'll start with section 9.3. Worksheet number 15 is already available. A blank version of worksheet 15 is already available. It's for an introduction for series. So yeah, let's see each other again on Friday. Okay, bye everybody. Yeah, I need to run to my next class, at least virtually.